this talk on the topic, what is the distance in the arena of science at which the analytical solution to Navier-Stokes equation becomes available. Very first, myself, Chaudhary Hari Krishna Dande, I'm the first author, and we have two more authors over here, Chaudhary Shambhu and Chaudhary Shankar. These both are my brothers. When we were small kids,
Doctor.
no, I'm just master's, postgraduate. I'm still not a doctorate. Okay. And so Chaudhary Shambhu and Chaudhary Shankar, these both are my elder brothers. And when we were small kids, we used to talk about resonant properties of water, the properties of cosmos in general, and the words that they spoke in those days, I haven't yet found any such proof in literature, but they have been widely discussed. As a reason, I have placed them as authors. I put up my own company, Ben Services Corporation Limited. It's in London, and it's largely a paper company so far. We are still to open up full form. Again, thanks to St. Petersburg University, the organizing committee, for inviting me here. It's on the third occasion that I've been over here. On the first two occasions, I tried to come, there were so many problems, and on the third occasion, the day I was about to move, one day or for one reason or the other, my hand got fractured. It was on 10th of June. Next slide, please. Okay, now I raised my memory back to this problem to the year 2001. I was a postgraduate student at Indian Institute of Science when my junior, Mr. Jayant Mukherjee, he introduced me to this problem. He told me, look, if you solve the analytical solution to Navier-Stokes equation, it's the Nobel Prize. And yes, I was very energetic, highly enthusiastic. I thought, oh, is it a Nobel Prize? Hold on. For 30 days, I literally sat down, and when I looked inside the Navier-Stokes, to my startling revelations, I find out that there has to be partition of space if we come up with a solution. There has to be supersymmetry inside there, and there has to be partition of space, supersymmetry, and yes, there has to be point-cut geometry. The three-dimensional point-cut geometry needs to make its appearance. Next slide, please. Now, the Navier-Stokes equation, largely we have these conservation equations. It's based on the equation of Newton's second law, where, next slide please, where Claude Louis Navier and Sir George Gabriel Stokes, these both, they came forward, and in the year 1822, they came ahead developing the equations of fluid flow. This particular equation that I've displayed is simply for an incompressible flow, and here you see the equation of continuity, and above you see the Navier-Stokes equation. Here we have three unknown components of velocity and one unknown component of pressure. That is, in total we have four unknowns. Next slide please. Now, people, they have tried. Yes, one slide back please. Yep.
Next.
Yep, next slide please. Okay. Now, there have been so many people who have worked on Navier-Stokes equation. Putting up entire literature would consume a lot of space, but a few of the literature that I have found is what I have placed. Theorem of Leray in 1932, for every time greater than 0, there exists a weak solution in the sense of distribution of Navier-Stokes equation, and it satisfies the following condition. This is very complex, I won't go into details. And then we have Ledizynska inequalities, and this is the most interesting part. She worked out for the two-dimensional flow, and when it came to the three-dimensional flow, it's here. We take a look over here, 1/4 and 3/4. The norms here are different, and the norms being different, it's really very difficult to solve this problem. Now, let's get to the work of Edristiti. Edristiti, it is a talk recently at International Center of Theoretical Physics in 2016. In his talk, he has exposed the problem. What is the problem which is solved? The smoothness of Navier-Stokes, smoothness of the solution of Navier-Stokes equation becomes possible. This is simple. Is this integral finite for any given time t, starting from any form of initial condition? We arrive at this solution, we declare that this is finite, and yes, as far as the Clay Mathematical Institute, they have declared a $1 million prize to this problem would be solved, but it's not that easy to solve it. There's one more reference that I would like to include about Professor Terence Tao, who for an average three-dimensional Navier-Stokes equation has displayed that the equation blows up in finite time. Let's go to the next lecture. Next slide. Okay. There is one big development. In the year 2001, I did not know anything about point gauge geometry, but it was the year 2002, if I'm right, when Gregory Perelman, he had set up, he had put up something in his papers about point gauge geometry, which was realized way later in around the year 2012, 2013, as to be the solution of point gauge geometry in 3 dimensions. I have a simple question. You have an analytical solution to Navier-Stokes equation. No matter what the solution is, it has to be universal across geometries. So any geometry needs to be constructed. So you have a solution. That solution has to be evolutionary in nature when it comes across geometries. So any claim for analytical solution to Navier-Stokes equation valid across geometries of 3 dimension has to contain the 3-dimensional point gauge conjecture as its inherent part. And this development so far when it comes to the frame of Navier-Stokes equation has not been displayed in literature simply because no one has come forward with a solution. This acknowledgement has still awaited attention, for we are still to realize an analytical solution to the problem. Next slide, please. Okay, now let's have a fresh look. Let's take a look at what the Navier-Stokes equation is, how complex the problem is. We have a bottle of water. We roll this bottle of water, and at each and every location in this bottle, can we declare the velocity fields? Can we declare the pressure fields? The question is this simple. Literature has concluded that yes, there have been tries, but yes, we need some new ideas. We need some new approaches. What can be the approach? A simple approach. PDE, partial differential equation, and ODE. In ODE, whenever we have solution in finite spaces. Whenever it comes to partial differential equations, the solutions are in infinite spaces, and there is where the problem is. So why not convert the PDE into ODE? Yes. We may get over here, take a look at this property of time, get an expression over it, and well, would we be able to move a step further in this direction? Maybe, maybe not, but that's a path. Anyway, let's take a look. If we have to identify a space in which the PDE has the solution, then we identify the characteristic of the space in which the solution exists, and from those characteristics, we attempt to revisit the problem and, in other words, gain a better level of certainty to solve it. That is, we go ahead defining the stepping stones on which we step properly, and then we dance around simply to get the solution. Next slide, please. Okay, now we take the Navier-Stokes equation if we have to solve it. Okay. This is a fluid particle at A. Fluid particle moves at B. Fluid particle moves at C. Fluid particle moves at D. At each of these locations, what's the velocity field, what's the pressure field is what we need to answer. But rather than going from the classical viewpoint, let me throw this problem in the world of quantum mechanics, the Schrodinger cat problem. Well, the fluid over here could have gone over here, it just went over here. So what I do, I define a wave function and declare that the wave function moved, it went ahead collapsing over here, it went ahead collapsing at C, it went ahead collapsing at D. How did the wave function collapse? This question is the question of quantum world. No one has been able to answer it, and if we are able to answer it, then yes, we have made a massive stride. My further question is, if we are able to answer A moves to B, and before it has reached here, at this location, if we identify a plane where before the event has occurred, we arrive at a solution that yes, the wave is going to collapse at point B, the wave is going to collapse at point C, the wave is going to collapse at point D. Before it collapses, we have made a massive development. Now to this massive development, I would like to add another development. These cats, let me put the Schrodinger cat at each of these locations, and are all these cats being controlled by a master cat? Maybe inside the bottle, maybe outside the bottle, depends upon the geometry taken. And if we decode the master cat as the controller towards each and every motion of particles from A to B to C to D, so on and so forth, then would we have answered the foremost question of quantum mechanics, and thus can we arrive at a conclusion that an event can be told before it occurs? That's it. Now, can from the world of quantum mechanics, the second major challenge is, can from the world of quantum mechanics, the Navier-Stokes equation be derived as a case where one of the extremities will be the limited Schrodinger equation? Further, if we are able to decode the master cat, what we have achieved, this is a big point, shall we have achieved at a function which can see across time? And the expression thus realized would contain an intrinsic solution of time dependency, which would be further helpful to linearize the Navier-Stokes equation, should one wish. Now, if we are able to look across time, then would it be an interesting finding to connect, would it be interesting to connect such a finding to P versus NP problem, which is another millennium problem declared by Clayton Mathematics Institute? Here what I intend to say is, when we are trying to find an analytical solution to Navier-Stokes equation, somewhere or the other, the P versus NP problem would make its appearance. Next slide, please. Okay, so end of the day, what I was saying, I was just trying to say, when we move from A to B to C to D, we are moving across events, or we are defining events. Okay, event in quantum world, event in classical world. Let's take a look. When a particle moved from position A to B to C to D, I can call them an event. Okay. When the universe came into existence, there were two brains that collided. Literature says that. I don't say that. Even that was an event. Okay. Across, when the universe started forming, across formation of the universe, various constants of the standard model came into existence. Appearance of these constants, are they all event? A hurricane repeatedly occurs. Is that repeat of an event? A tornado occurs. Again, this is an event. Earthquake, train crash, plane crash. So, end of the day, the fundamental underlying principle that connect these events, are they one and the same? One may be a higher complexity level problem for the other, but are they one and the same? Now, across each of these events, if we connect a master cat, in other words, display them in advance, how and where the wave function is going to collapse. Before the wave function collapses, then have we built an early warning system for these portions? These are all wave function collapsing. So when we are taking a look at bottle of water from point A to point B, the question is not this simple that, well, what's the velocity field, what's the pressure field? The realizations are this large that we can get ahead to build an early warning system. Now, can it be possible to declare the events year in advance across such time scales, and if so, would we have thrown more light on trying to solve the simulation hypothesis of whether we exist in a simulation? If so, what are the limits towards such an existence? Is this a beautiful industry? And does it have a potential to be a multi-trillion dollar industry? And here is where Clay Maths Institute is justified in declaring $1 million as the price for obtaining an analytical solution to Navier-Stokes equation. Taking once again, if I were to explain the first paragraph over there, in Russia in the early 1900s, there was a meteorite crash. A large portion of Russia was destroyed. What happened over there? Again, there's no much detail. A few years back in time, again there was a small meteorite that crashed. The question that I raise is, at that point in time in the year 1900, could it be decoded that in this around the year 2010, I don't remember the exact year, around the year 2010, the next meteorite crash will happen. If we are able to solve the wave function, then yes, in my opinion, it may be possible. Next slide, please. Okay, now, how far in science can the Navier-Stokes equation track? Sir Roger Penrose, he has been able to look across universes using conformal field theory. This I obtained from one of his lectures that he had given. What he did, he has used conformal field theory to override the initial singularity problem that connects across universe. Say we have a universe B, it was into existence, it went ahead, it closed, and another universe A came. Over here, the initial singularity, he has closed them using conformal theory. Now, when I'm taking a look at the wave function and wave function collapse and identify a master cat, can the master cat look across time, across universes? Can event across universes be looked by the master cat? And thus, before the wave function collapse is observed, shall we be able to peek across the universes? This big is the implication of Navier-Stokes equation. Next slide, please. Now, when we are trying to solve the partial differential equation, what we are trying to do, we are trying to construct the space in which the solution exists. The topology of the systems needs to be defined step by step. That's part of the problem. That's and over here we go ahead for the Bolzano-Weierstrass theorem. This is the key. We find that in a PDE the norms are different, and same is not the case when we come to an ODE. I take your kind attention to the previous slide where we had the norms as 1/4 and 3/4 for three-dimensional system, and where for two-dimensional system it was half-half. Let's go to the next slide, please. Next. Yeah. Now the best of the question, and can we get to a solution? How do we construct the space across which the solution exists and define the necessary axioms? I bring David Hilbert to my rescue. I have made the problem big, I have made the problem complex. From classical world I enter to quantum world, from quantum world I enter across universes, and now David Hilbert to my rescue. Hilbert's sixth problem is to axiomatize those branches of physics in which mathematics is prevalent. Can the same be achieved right from the initial state of the universe and the axioms be identified across various stages of the evolutionary state of the universe? Be it quantum, be it classical. The necessary topology be constructed, and once it transitions from quantum to classical world, obtained at interface of these two worlds, would it display the grand unified theory? So once we are trying to solve this, are we getting this far? There is a wonderful opportunity over here. Rather than simply saying that, okay, let's say if somebody comes forward saying that yes, he or she has obtained a solution, analytical solution to Navier-Stokes equation, or has found out smoothness, then why he or she should not get this? We should get this. Is this the right candidate to solve the theory of everything? A beauty of this part would be the origin of viscosity in three-dimensional Navier-Stokes equation that has caused issues to so many researchers while they have attempted to solve this problem would be realized from topological space constructed. Here what we are doing, viscosity has caused a problem when we are trying to solve the problem. We simply don't take a look at viscosity. Initial state of the universe, I identify a wave function collapse, I construct that topology. Next stage, again how the universe evolved, I construct the next topology. Bring that to the bring that to a transitionary stage from quantum world to classical world. Classical world, we have general relativity. General relativity fits into the geometry of quantum geometry. From there is where I transition, and from general relativity I bring further come down to the Navier-Stokes equation. So, and when the geometry evolves, the geometry within it would display the presence of viscosity. I need not run with viscosity and try to solve the problem. When geometry displays viscosity in it, geometry displays the stress strain tensor in it, my equation is equal. So let's, rather than taking a look at the equation and from the equation trying to solve it, I go to the axioms. From the axioms, I go ahead constructing the topology, which is the requirement. And from there, in the constructed topology, yes, here is where the viscosity is, here is where the stress strain tensor is. And the problem that has been exposed by Navier-Stokes, whether the integral is finite, I find a gradient across across the topology constructed, which may be the solution. Next question. Next slide, please. Okay. Now, how do you define the axioms? We see these are numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have some decimals. This is some sample I've just written. Can we have a topology that connects all this? Are these all connected? If we are able to get this far, which in my opinion I've been working on, and in those days, in my early days, I did make some findings here, then we have achieved the wave function collapse from the initial state, and the evolutionary nature does make sense. Once an evolutionary nature of topology of space is constructed across these numbers, question again raised is, shall it be possible to reach the absolute initial condition of the universe, irrespective of the answer to the question whether the universe is cyclic in nature? Can we get across the initial state? And the cat does it all. Next slide, please. So, what are the efforts so far? While attempting to construct the space in which Navier-Stokes equation solution exists, properties pertaining to wave function collapse are being realized, where it would be reasonable to say that disasters can be foretold without aids from any kind of devices. And such, whenever a solution is achieved, the achieved solution needs to be checked for such class of consistency. What I mean, if you come up with a solution to Navier-Stokes equation, that solution should display to you disasters in advance, or it should go that far. If you are not growing your solution that far, or if your solution cannot track that far, means your solution has some error or has some shortcomings. It may be possible to define and declare occurrence of disasters in form of wave function collapse and declare them beforehand. Here is where I am the best. Maybe several hundred of observations across the world have been done towards such disasters to have occurred across decades. What I mean, before disasters occurred, one way or the other, I was able to connect to them. I was able to declare them beforehand. It is possible to computationally declare disasters before they occur, subject to appropriate topological construct being readily available. Next slide, please. Okay, let's conclude. So here we are. Whenever an analytical solution to Navier-Stokes equation is obtained, for it to be complete, the following postulates needs to be verified. A solution to this problem would contain the three-dimensional Poincare geometry as its inherent part. Insight on the P versus NP problem would be connected. Insights into how space has been partitioned since the time the universe or megaverse got formed with presence of supersymmetry would be revealed. The solution should display the theory of everything, or if not everything, the grand unified theory, the least. The space in which solution exists is in high dimension and has the property to compute across time, and when followed would be faster in computation when compared to the solution mechanism being followed by computations of traditional equations. A calendar system to forecast natural disasters would be easily possible, and a fundamental approach to this problem can be better understood when we understand fluid flow from the world of quantum mechanics, and once the world of quantum mechanics is fundamentally answering the Navier-Stokes equation and unifying the quantum world to classical world will become a further easy task. This lecture that I have given is first of my series, where today I have tried to define the stepping stones on which I will be trying to work out the solution. Next slide, please. Thank you for your kind attention. My name and feedback inputs over me, all on me.
Thank you. Any questions? I would like to make a question.
So,
Chairman, as far as I know, Claude Navier and George Stokes were very practical persons.
so
All many bridges are built on the supervision of Navier and Stokes derived this phenomenologically viscosity.
yeah.
How can we expect that viscosity may be derived from quantum mechanics? I can't understand.
Yes. Beautiful question. How viscosity can be derived from quantum mechanics? What I said, when it comes to the world of quantum mechanics, let's say I come up with an initial topological space for the initial condition.
Just if you can answer shortly.
Yes, in short. This topological space, at the interface of quantum and classical world, I bring it to the level of Poincare geometry, which is at the level of general relativity. And from general relativity, I take further down to the Navier-Stokes equation, where viscosity exists. So I'm not ruling viscosity out. Viscosity is there, but as the topological construct has evolved,
Stokes showed that viscosity is a consequence of statistical movement of molecules.
yes,
And why we need quantum mechanics?
there is where the continuum approximation would come into play, and viscosity would make its appearance.
Thank you very much. And we have